Okay, well, the conference is being recorded. So why don't I get things started here?
All right, thank you. I'm going to drop out and probably check in later.
All right. Well, today is October 14th, 2017, and this is the John Chappell Natural Philosophy Society Saturday Science Chat. And please go and visit our website and our Facebook and visit our forums. Although a lot of the conversation just happens on email, so there's like a group of like 54 people or so that somehow managed to get onto this email list, and we send messages, lots of messages, every day to this group. There's a little bit mystery on how you get on this group, and even a bigger mystery on how you get off this group. Because if you get on, it's very hard to actually get off, and there are a lot of messages, like 20 a day. I try and keep up with it, but it is difficult at times. But so for this Saturday's chat, there was a topic that came up, which is very much a mystery, which is how unipolar induction motors or generators work. And this has to do with the nature of the magnetic field. And this came up because some people were challenging my conception of the magnetic field, about like how do you reproduce this Q cross B behavior, and or things like induction. And I will have to admit that my own theory doesn't cut it. That there is still something that's not right that can fully explain this whole Lorentz force law thing. I mean, it's so confusing that I had to actually make myself a little helper here, which is my Lorentz force law helper, which shows that the pencil direction is the electron motion direction. And then this tag here would be the magnetic force direction. And then the actual resulting force is what this tag shows. So it's kind of crazy that when electron moves this way, basically the force goes out that way at a 90-degree angle, and also at a 90-degree angle to the magnet. So if we practice this a little bit, like if my arm is a wire and the current is heading towards you guys, and I point my pencil so that it's heading that same direction, then by the right-hand rule, which is you got your right-hand rule, you put your current in that direction, and then your fingers show what direction the field is going. So the field is actually circling around my arm that way. So my tag here, I have an arrow here. I put the tag there, and so if it's flowing in the same direction as the wire, then my force tag is actually pointing at my arm. So that if the electron is going this way, then the electron will go this way. Of course, now the mysterious thing is that if the electron is going the opposite way, then that changes the direction of the force to be opposite. So the electron will be deflected away. So depending on whether you're going with the current or away from the current, the direction of the force is completely reversed. Now that is very difficult to understand.
So are you talking about Lorentz force and
Yes.
the issue that it has with the Faraday paradox, right?
Yes, but you do need to understand how this works before you can.
Yeah. So my point would be actually, I would suggest actually that one thing is how electron behaves in the magnetic field, and the other is how say the magnetic field influences the structures of the conductor. Free electrons, say, in the conductors. There should be totally different thing. I think.
Well, maybe.
I mean, just suggesting that kind of to think of. keep
Well,
in
I
mind
want
maybe.
you to keep. I want you to think about your suggestions because I'm going to show the video and maybe some other videos, and then I'm going to leave it up to you guys to
Could
try to
you
figure
send
out how
could
this
you send
works.
the link, frankly, sorry, links for videos by email? You know, because as I said, maybe some other people as well. I'm attending the conference per phone. You know, so I'm
Yes.
not on the. But I have laptop next to me, but cannot connect to the conference by internet. You know, for my computer for some reason. I don't know.
Well,
So if
the
you
initial.
wouldn't mind just send, you know, when you show the video, just send the email. I mean, kind of a link by email.
All right. Well, we'll see if we can keep track of that. Actually, I don't think I can because I have to use MailChimp, and that's very complicated. But let me see here. At least I can put in the chat the link to the video. But if you're following along at home, I believe you go on
It doesn't work for
YouTube.
me.
If you go on YouTube and search for this video called Faraday Paradox Unipolar Dynamo Demo Part 1. That's the video I'm going to be showing here. So let's go and I'm going to show that video here. Now, basically, there's just music, so I'm just going to talk over the video since there's really no point in doing that. But let's get the video started. Let me share that out. Get it go full screen. So this is only about 3 minutes. And let's get it going here.
The kind of noise that the people in Cuba must have heard.
So here the disc isn't even moving.
The noise is about the noise that the people in Cuba must have heard.
Okay, so that is our first video. So what did you think of that? Did you understand what was going on there?
What's the mystery?
So,
I don't see any mystery there. There's no paradox. The magnet sets up an environment through which the disk moves. If the magnet,
Just a moment.
whoever is not talking, please mute your microphone so we don't get the feedback. Anyway, so if the magnet rotates, it's not changing the environment that the conductive disk is in. So I'm not seeing why people call it a paradox, unless you go back to the old magnetic field lines, and the magnetic field lines are supposed to move with the magnet. Yeah, then you have a problem. But if you don't assume that, there's no problem, there's no paradox. It works out fine.
Yeah, I think that that is certainly one conclusion you can come to. Actually, when I looked at this myself, I pretty much came to the same conclusion that the magnet is just setting up, we're looking at our Lorentz force law. The only thing that really matters is the direction of the magnetic field. It didn't really matter whether it was moving or not. The only thing that seemed to be mattering whether it was moving was the electron itself. So it made no difference to Lorentz force law whether the magnetic field was moving or not, because there is no motion vector given to the magnet, only a direction. So I would kind of agree with Bob that if you were going just strictly by Lorentz force law, then at any given moment...
Wait a minute. Here you go.
Go ahead. Harry, we're having a little bit hard time hearing you.
Nonsense again. The Lorentz force law requires a velocity. What's the velocity with respect to?
That would be the laboratory frame.
And the V of the Lorentz force with respect.
Harry, you're breaking up. Is there something?
That's the paradox.
We're having a really hard time hearing what you're saying. You're kind of breaking up.
maybe you are too close to the microphone over.
Talking about, do you? Yeah.
Well, I think your main point is that for people who think that this is a problem, is that you'd have to figure out what the velocity is of the electrons relative to the...
Franklin, if you're talking about first configuration here, right? Everybody is talking about first configuration, right?
What is the V in the Lorentz force formula? What is it?
The velocity is the velocity of the electron.
Velocities are always relative. Velocity is relative to us.
So are we talking about the first configuration where only magnet rotates?
No, the only confusing configuration is the one where both the magnet and the disk rotate together. That is the configuration that people
What
feel
about
that
the second one, when only a disk rotates? Is that fine for you?
There is no paradox there, because you can clearly see the velocity of the electrons in the disk.
Mm-hmm.
The only question is, the only place where we have the paradox is that when the magnet and the disk rotate at the same time, because in that frame of reference, you could say that the electron has no velocity.
Yes.
And therefore
but it has, if you look at the electrons, they have velocity with respect to the collector, right?
yes, that's that. With respect to the collector, they would definitely have velocity.
Yeah. My point would be here actually that we should not be looking only at the Lorentz force. We should be looking at the longitudinal component of magnetic field in a way, kind of divergence part, and kind of it may come out. By the way, I mean I'm talking about this and considering from the point of view of Artsukovsky's heterodynamics. By the way, this seems to be the only situation where Artsukovsky did not come up with a solution. Maybe yet he's in his late 80s now and so on. But I was looking some materials, maybe some part of book or some comments, some 10 years ago. He was saying clearly that he could not get it. But you know, other people couldn't get it, and for many problems that appear, that people ask him, he used to say, okay, there are principles, you can look into it, think about it, work with it. So as a continuation of that, I would suggest this kind of aspect. He has non-zero divergence of B and D in his extension of Maxwell equations, but he was not working with vector magnetic potential, for example. And the divergence of A that comes out maybe directly from non-zero divergence of B and D and so on. So here, I've been looking last couple of days since this was actualized, in a way that actually situation becomes so that those collectors simply kind of shovel up the induced how say structures on the surface of the disk, above the disk, and so on. So I would like to know, for example, what happens if we reduce the separation between those collectors, or when we increase velocity and things like that. You know, I would be thinking of some kind of really kind of dynamics in terms of angular momentum and difference of densities of those. Say charges of those structures on the surface and so on, so that we have actually maybe having actually just shoveling up of that energy flow.
Well, I think you mentioned that it kind of depends on where the connections are to the disk.
For example, just would wonder. I mean, I would assume that if direction is, of course, I mean, the distance is reduced, then the effect will be smaller, things like that. But
well, the thing that I can kind of understand and agree with Bob that everything works out fine, but the video showed one case I'd never seen before, where they kept the magnet and the disk stationary, but they just moved the stator around.
Okay, you just stator is collector. So when I'm referring to it, so it's just showing up. You have always dynamics. Even if the magnet is static, when you have B, the B that we are kind of looking conventionally is the measure of rotation of certain structures, certain energy flows of that form. So we have dynamics all the time, but that dynamic is kind of in the equilibrium. So with everything is quiet, nothing happens. But once we start moving that collector, right, or then we kind of I came up with this kind of term, shoveling up actually, continuously by that very movement of the collector.
Yeah,
because
so
we already have dynamics. To which extent now the effect is due to the Lorentz effect as a rotor or curl of A, or as a result of scalar potential, vector potential kind of divergence of A, But we are actually disturbing this kind of equilibrium and just picking it up, and just that energy goes up and down of those collectors. Maybe, you know, that's the main process. Maybe it's not important, would not be of the same kind down on the surface or certain region of surface of the plate.
Right. I see we've
You know,
got
but kind of really kind of just
question from
sucking up or showing up and down. You know, this would be, in my view, kind of how to say what is going on actually.
All right. So Ian, did you have a comment? I'm not sure we can hear you though. I think we've been having problems with your audio. Maybe you can put your comments in your questions in the chat, because I don't think we can hear you, Ian. Your microphone is on. Okay, I think we're just gonna have to wait for Ian to send his message in the chat. But I did want to ask Bob. So Bob, I was wondering, can you explain the situation where they just moved the communicator on the stationary magnet and disk, and that generates electricity? What did you think about that?
Through the magnetic field. But I'd actually take the analysis in a completely different direction and use Weber's electrodynamics and Weber's force. And when you do that, it turns out that the force is proportional to the acceleration. And of course, you have a mechanical transfer of energy from the disk. Something is mechanically rotating that disk, translated to the electrons or the conductors within that disk, giving it an angular rotation, therefore an acceleration which is radially in or out from the rotation axis. And it's that radial acceleration in or out that when you do the integration, the path integration around the closed conductor loop, which gives you the EMF around that conducting loop.
Is that true
So,
even when both the magnet and the disk don't move, like when they just move the stator?
Well,
yeah,
that's
why not?
part of the conductive path, which is moving, and therefore has a radial acceleration.
So I think it's something along the line of what I have been talking. I just wanted to kind of refer to, I don't know, to what extent you have been getting my view.
I see, Bill. Bill, you raised a flag. Do you have a comment?
Yes, the answer to these questions was discovered by Winston Bostick when he did his experiments with the plasma or electromagnetic field. He was able to make what were called solitons, and the solitons are the building blocks of all elementary particles, and they are made from the electromagnetic field. So whenever you have anything that is moving with respect to something else, you're going to generate a current. Whether it's the collector or the magnet or the disk or whatever. And because the electromagnetic field from the matter in any of these things is permeating all of the space in that area. And
yeah, that makes sense.
And you see this was done when people put they wanted to measure the motion of the Earth through the ether. They found that they could measure the rotation of the Earth just by running a light beam in two different directions in a closed circuit. They could see the difference. And so we've known about this for quite some time, but people using different philosophies of science and ignoring certain experimental data find they can't explain some data that you're talking about today.
Let's see. I thought I saw Ian's signal come up. Ian, can you say something?
I don't think you can hear me. Can you hear
No,
me?
actually, we can hear you now.
Oh, can you? Oh,
Yes,
excellent.
we can hear you
I don't know
now.
what I've been doing. I've been playing around. Okay. Well, I said a couple of things, Franklin, which you didn't get. One was there's a second part to that video. The video you showed is actually a very good exposition of the problem. But there's a second part, I think the link to which was posted by Ian Montgomery. Now, the second part, I think, is a bit more questionable because it seems to be confusing the essential problem with that of, say, the Truton Noble experiment, where you have a capacitor being carried by the Earth, if you like, and you're expecting a deflection of the plate. It's a bit like the ether problem and the whole question of absolute space and so on. But the essential point here is you correctly talked about the surprising nature when the magnet and the disk are co-moving and you're actually getting an EMF. Well, and you also mentioned this fifth experiment, which isn't shown so much, where they're actually moving the stator. In other words, they're moving the circuit, the external circuit. So there's the key. It's the relative movement of the magnetic lines of force and the external circuit. So if you think about the first paradox, if you like, where the magnet and the disk are co-moving, they are actually the lines of force which are moving with the magnet. We can postulate they are rotating. They are actually cutting the external circuit. The external circuit, the wires from the contact brushes going back to the galvanometer, actually cutting that. So you're getting an EMF. And similarly, when the stator is moving, well, those cables are actually cutting the lines of force. And then it also explains the paradox where the magnet is moving alone and you're not getting any electromotors induced because though it's moving with respect to the disk. Well, the simple explanation there is it's actually inducing an EMF in that case, but it's also inducing a counter EMF in the external circuit, and the net result is zero. So I think we're going there. Some emails have come in recently, which I've just looked at in the last 10 minutes. Very, very complex. All these etherite dynamics and circuits and div and curl and everything. But I mean, I'm trying to concentrate on this one point that what has been neglected heretofore is the effect of the relative movement of the lines of force, the flux cutting, if you like, against the external circuit. And Kelly has a couple of diagrams about that, which, if necessary, I can try to scan in.
And this is Harry Ricker. The problem with that explanation is there have been numerous experiments, beginning with Faraday, that remove the field effect from the external circuit, and the EMF is still produced. So the experiments that do the shielding of the external circuit kind of argue against that interpretation.
I've read those too, yes.
Well, how do they shield?
You might be able to give us a link to those because I'm not quite familiar with those shielding experiments.
Because I can't. Because
well, what they do basically is they concentrate the magnetic field into, like the magnet would be in a iron enclosure, and so what they do is they make the magnetic field flux only at the point of the moving disk, so to speak, and there's no field external. Actually, Faraday did this in his original experiments, and what he did was he moved the external wires around and put them in different orientations and found that that had absolutely no effect on the result.
Actually, Harry, your paper, which you have resent, is very, very detailed, as I've said on previous occasions. And I haven't read it recently, but I take it that it includes all these references that you're referring to now.
Well, it's not complete. That's one of the problems. I think I talk about the Faraday. Faraday did this in 1851 or 52. And he tested whether or not the flux was being induced in the external circuit, as I said. And what he did was he tried to make the external circuit, the wires were such that they were they were not in the direct anywhere near the magnet. And he moved the wires around in different orientations to test whether or not the induction was occurring in the external circuit, and he found that it wasn't. And that's pretty much been confirmed by experiments since the more recent and modern experiments.
But on the other hand, Kelly has performed two experiments. One in which the external circuit is composed of wires merely in parallel with the feeding circuit. And in that case, you have a cancellation when the magnet alone moves and you get zero EMF. But he then also makes the return circuit part of the disk itself. And then he finds there is an EMF when the magnet alone moves. So he concludes from that it is actually induction in the external circuit. So again, part of the argument.
Well, that doesn't, the problem is there have been numerous experiments. Miller did experiments, which are very comprehensive. And then this Argentina group did experiments in which, and they all, Kelly is right that the magnetic field does move with the magnet. Okay, and the experiments generally tend to confirm that. The explanations that have been offered that the EMF is induced in the quote external circuit have been tested in numerous experiments by Mueller and the Italian group, the Argentinian group, and of course Faraday had already done those experiments in 1850, and so all they did was confirm Faraday's null result.
But do all the experiments, are they consistent with the frame of reference being considered the frame of the stator? Because that's what it seems to be, that the only frame that really matters here is the frame that's got the stator in it.
The bottom line is if you take the frame of reference to be the frame where the galvanometer is, okay, then if that circuit there, if you assume that circuit's at rest, the collector circuit, as Slobodan calls it, then that becomes the reference frame. And if you measure V relative to that reference frame, then you can apply the Lorentz force and get the right result. But it's sort of an artificial thing because the magnetic field itself has no motion in that frame.
So if we made a new experiment where we put the galvanometer in the same, we made it so that the galvanometer circuit itself rotates around, then we would predict that we would not see any EMF in that case, actually, no matter.
No,
right?
You get an EMF. I think that was demonstrated in the video.
No,
Kelly did that too, if I'm not mistaken.
Experiments.
No, I'm talking about if you take the galvanometer itself and you spin that thing around.
Yeah, the external circuit is spun around. And when you do that, it counteracts the previous results. So in other words, when it isn't spun around and you don't get an induction when the magnet alone moves, well, then you do get an induction in the opposite sense when it's spun around. And similarly, when you have the magnet and the disk moving together and you get an EMF when the external circuit is stationary, if you like. But when you move it around in the way you're suggesting now, that actually cancels out and you get a zero effect. So I think those experiments are actually listed.
I think that's shown in the video to be producing an EMF. Isn't that correct?
No, that was you just moving the stator around, but the actual circuit was still stationary on the laboratory bench. No, the meter itself.
So they didn't move the circuit?
They didn't
well,
move
there are experiments where the external circuit is moved. There are experiments where the external circuit is moved and you get an EMF.
Even if you spin it around with the discs and such, you still get an EMF in that case. Because I'm not quite sure how where
an EMF whenever there's a difference. let me make this statement very clear. You get an EMF when there is a motional difference between the stationary circuit and the moving part of the circuit, and the moving part of the circuit is exposed to a magnetic field.
And it still never matters whether the magnet is moving or not. Generally
Correct.
speaking, it doesn't seem to matter whether the magnet's
Now,
ever in motion.
that's true in the circular case. Now, here's where it gets confusing. That's true in the circular case, but not in the linear case. So if I have a linearly moving magnet, that doesn't happen. The motion of the magnet does have an effect. Okay, so you get a different situation than you get in the circular motion case, and that's kind of confusing as well. So only discussing the circular rotation case and not looking at the linear motion cases isn't really. So your theory might explain what happens in a circular, rotating magnet type situation, and then your theory might fail if you try to apply it to a linear motion situation.
Well, I believe in the linear situation, you would be talking about actually varying the strength of the magnetic field as it goes closer and further away. And then we would start talking about just induction. I mean, you challenged me to explain how induction works, of which the simplest would be you have a straight wire and you have a magnet and you bring the magnet close to the wire and then you take it away. And that by itself generates an EMF, right? That would be the simplest example of induction, right?
The issue here, the problem here is that there's a lot of experiments, okay, that have been done, and pretty much what they do is they confirm what Faraday had already done in his book on the experimental researches in electricity. And there really hasn't been much of anything really new that's contradicted what Faraday or added anything significantly new. What has been done is they've eliminated different theories. Okay, what people have done is they've examined particular interpretations, theoretical theories, and that's generally presented a lot of problems for all the different theories because there's no particular one theory that explains all the cases.
This is Bill Lucas. There's some experiments you all are not taking into account. William Hooper at University of California at Berkeley performed a number of experiments on electric and magnetic fields, and he measured 14 properties of electric and magnetic fields, and he found there were 3 types of electric fields and 3 types of magnetic fields, and one of those 3 types could not be shielded in any manner. You all don't.
Well, Bill, I looked at that, and I don't really see that Hooper has done anything different than anybody else has. It's just
he has measured the properties.
Method of experimentation.
You see, current.
So we know pretty much what the experimental facts are. What the difficulty is coming up with where people agree upon what theory satisfies all of the experiments. That's where the disagreement is.
Yeah, well, it turns out that the complete set of the empirical equations of electrodynamics, what were originally called Maxwell's equations, but then Oliver Heaviside redefined Maxwell's equations to be only 4 of the 6 Maxwell's equations. But if you use all of them, they explain all these properties better than what the current Maxwell equations that Oliver Heaviside worked with do. And the one Oliver Heaviside assumed that all electric fields are the same type and all magnetic fields are the same type, and there's no difference between them.
Well, I wanted to ask Harry. So, Harry, do you still see amongst all these explanations a paradox, or does this seem solved to you? And if so, what is the solution in your mind?
Well, what do you mean, paradox?
Well, do you see a paradox? Do you see that there's still something that is not explained by all the explanations that you're aware of?
Well, they're not, they don't, it depends on what explanations you're referring to. I mean, all explanations is sort of all-inclusive.
Well, let's just take, so
As
when we,
I've
when we
said
started out,
before, basically, I've said before that if you use the flux change law, you really don't have a problem.
you mean the flux line theory? I thought that one is the one which definitely has paradox.
The flux change law says that when the flux enclosed within the circuit changes, an EMF is produced.
Well, not quite. I mean, I would say that it's actually the flux which has to be cut. You can actually change the flux within the circuit itself, and if it isn't actually being cut or there's no variation in that, you won't get an EMF. And this is why you're getting a sort of a cancellation of effects. You're getting, you're getting a flux increase in one part of the circuit, you're getting a flux decrease in the other. But when the net effect is a flux cutting, if you like, well, then you do get an EMF.
Well, what Faraday did was he took a circuit, a wire connected to a galvanometer that created a complete circuit. Okay, and then he moved part of that circuit across the pole, one of the poles of a magnet, and an EMF was produced on the galvanometer, and from that he created this flux cutting rule. But that only says that the flux contained within the circuit, okay, when you integrate the flux around the circuit, was changing when you move the wire.
Well, I think we could probably all agree with that. That is the basic, induction experiment. But how does that exactly apply to all these spinning disks?
Well, the spinning disk, according to Faraday, is cutting across the lines of magnetic force, as if the disk was a moving wire moving across the face of the magnet.
But we were noting that basically the rotation of the disk doesn't seem to matter no matter what experiment you apply.
Yes, but the flux is still changing with respect to the fixed galvanometer.
Well, if the motion of the magnet doesn't seem to move, that doesn't seem to matter, then that would be an argument that the flux isn't changing when you rotate the magnet. It would seem that whether the magnet was still or rotating, the nature of the magnetic field above that magnet remains the same.
Yes, but the disk is moving.
Yeah, so the disk is moving. So that may be a significant clue. I mean, in the argument as to whether the magnetic field lines are dragged along the magnet, along with the magnet or not. I mean, that's an interesting question. So if you have a magnet, and you just think of the flux lines pointing upward from the magnet, which is conventional. And when you start rotating that, do those lines move with the magnet, or they just completely remain stationary to the magnet?
Numerous experiments have done that show that the field moves with the magnet because the field is attached to the magnet. So if you were to cut a hole in the magnet, that hole would be detectable with the absence of the field.
Well, does that mean that? I mean, that is if you change something about the magnet, like cutting a hole in it. But if you just take a magnet and you rotate it, is there any experiment that you can do that can tell a difference between the non-rotating magnet and the rotating magnet?
No, because you have to have a change in the magnetic field. If the magnetic field is altered so that there is no rotational symmetry, then you will find a change in the EMF due to the change in the flux as the magnet is rotating.
Do you see the postulate of a non-rotating magnetic field was introduced by Faraday in a sort of an ad hoc fashion, I think one might say, to explain.
That's correct.
To explain the apparent surprise, the actual surprise that you're getting an EMF when the magnet and the disc are actually moving. So I think the experiments actually do seem to indicate, the simplest explanation anyway, is that if you accept that flux cutting reduces in an EMF, well then the actual magnetic field is moving. But I'm looking here, Franklin, just at one experiment. I'm just reading it out now, but it's some chap by the name of Tilley, Tilley, 1968. Simple experiment here with a sort of a parallel circuit with two switches. In the first leg of it, you have a fixed cylindrical magnet, and in the second leg, you have a galvanometer. And he says, when the switch on the left, that's the one just beside the magnet, is closed and that on the right opened, the galvanometer circuit experiences a large flux change, but there is no induced electromagnetic force. He commented that Faraday's flux rule, the statement that the electromotive force induced in a circuit is proportional to the rate of change of magnetic flux through the circuit, cannot be applied indiscriminately. There was, Tilley says, and he's quoting again, a large rate of change of flux, but no induced electromagnetic force. He describes the test as a gross violation of the flux law, but offers no alternative explanation. And then Kelly goes on to say, this enigma can be explained by assuming that the basic cause of the effect is not due to the rate of change in flux, but to the actual cutting of the conductor circuit by the lines of force. In Tilley's test, where there is no alteration in the position or direction of the lines in relation to the stationary but alternating circuit, there is no effect. Just one example of that.
Well, numerous experiments have been done with respect to these types of paradoxes. And, that what they do in the engineering books is they give you a bunch of rules about when you'll get an EMF and when you won't get an EMF that sort of get around these issues. L.B. Bewley has written a book about this, and I don't know, are you familiar with this book? Flux Linkages, I think is the name of it, something like that. Electromagnetic induction and flux.
Yeah, it is referred to here. I'm not personally familiar with it, but he talks of Blondel and of Bewley, two experiments in this area which he referred to.
There's a whole bunch of, that's a whole nother kettle of fish. So you have to really understand what the experiment is doing. What it boils down to is you can't use a switch to change flux linkage. If you change flux linkages by moving a switch around, you don't get an EMF.
That's what this experiment basically says, yes.
And that's a well-established fact, yes. And so that's sort of an exception to the flux change law because you're not really causing anything. It's really basically moving the way the circuit is connected. It's not a motional change in the circuit, so to speak. You have to have a kind of emotional change in the circuit, either the magnet moving or the circuit moving, either expanding or changing in some way. And that seems to be the defining criteria. This is all discussed in a lot of engineering papers, and it's been hashed out ad infinitum. It's kind of, well-known fact.
Well, I'm thinking that, just thinking about the experiment, that there may actually be two completely different origins for the EMF. So, for example,
that's been standard engineering methodology. That's how they teach it in engineering schools, and they've been teaching that for the last 100 years or so.
I'm thinking that when the disk is moving, that the electrons that we're talking about that are actually cutting through would be the electrons in, say, the disk. But we're also talking about this case where you have that you consider the circuit of the galvanometer moving relative to the magnet. And I would think that that would actually just involve the electrons that are in the galvanometer circuit. So you move the circuit, you get the EMF, or you move the disk, you get the EMF. But I would think that those are two different things, or are they? I mean, that the case that still kind of stuns me is a case when you just move the collector around the stationary magnet in the disk, because I'm looking at it going, well, the electrons in the disk aren't moving. Certainly, it doesn't matter whether the magnet's moving. The only thing that's moving there is the galvanometer circuit.
Well, that kind of goes to what Ian was saying earlier too. I mean, that the experiment was done when you're moving the circuit or when you're moving it through the magnet, or you're moving the disk through the magnet, one or the other. So that coincides with what Ian was saying earlier too.
Well,
I want
my suggestion is to, if you want to, get into this whole issue, you just can't look at one set of experiments. You have to, there's a lot of paradoxes out there. There's all these, claimed exceptions to the rules. Whatever rule you set, there's supposedly somebody who's got a paradoxical experiment that refutes it. And, you can just pull your hair out trying to make sense out of it all, because you got a lot of conflicting ideas, conflicting experiments. One guy says this experiment proves my theory. Another guy has an experiment that he claims proves his theory. And it's just it's a huge literature. There's just tons and tons of papers out there, tons and tons of experiments, tons and tons of claims to explain it one way or the other.
Well, why don't we just start with the first claim that Bob made? So Bob's claim was that there's no paradox here at all, because if we consider the electron velocity to be relative to that of the laboratory frame, which contains the galvanometer, then everything works out, right? Because it doesn't really matter whether the magnet is moving or not, because that the motion of the magnet is not considered in Lorentz force law. And we see that the electron is definitely moving with respect to the laboratory circuit. So there is no paradox when the magnet is rotating with the disk, right? So is that a proper explanation for this problem, or is there a hole in that one?
Well, why don't you start with Faraday and not confuse the issue?
Well, I'm just asking, does that explain?
Faraday didn't say there was a paradox. Faraday never said there was a paradox. He had a solution. His solution was that the lines of force didn't move when the magnet rotated. Okay, that was his solution. He didn't say there was a paradox. The paradox arises because modern, somehow or another within the last 20 or 30 years, the mainstream people decided to call it Faraday's paradox. And why they decided to do that is kind of a mystery to me. But, my first question would be, why did mainstream change it from unipolar induction to Faraday's paradox, when Faraday never said there was a paradox?
May I just interrupt and thank you for that comment, because I see that physics, the mainstream physics, does that again and again and again. They make up their own verbology as to what somebody in history said or thought, and it's absolutely incorrect. And I think they did that in the case of a Michelson-Morley experiment. that was perhaps the worst case in physics, where they decided that since an ether didn't seem to affect something with regard to optical interference, that there was no point. Did that prove somehow that there wasn't an ether? And you go back to those who founded the idea of the ether. They never claimed that that they're the only thing that their ether is capable of doing is causing an optical interference. That was the least of the reasons for theorizing a ether. And by the time Einstein discovered that, I fear that the guy was too embarrassed to speak up and explain how he had forgotten what I just said, that the original ether's main task was not simply to explain optical interference. Indeed, the Greeks and others believed in ether, and they didn't note or care much about optical interference anyway. So we see this that mainstream will make a problem by fabricating history and fabricating the intent of the people who helped make history.
Well, Harry, that's a very interesting point. I think that unipolar induction was not a paradox to Faraday himself. He seemed to be able to explain it with very similarly to how Bob wanted to say, which is it's just a straightforward applications of a Lorentz force law with the electron speed being relative to the laboratory.
Well, remember now, Faraday there was no electrons or anything like that in Faraday's day. That came later, and that kind of presents some problems because now, when you bring in the electrons and try to explain things according to the Lorentz force law, now you're in a whole different regime of theoretical explanation than Faraday lived in.
Really? So
that's
Faraday,
why you get.
Well, Faraday didn't have access to the Lorentz force law then?
There was no such thing. Lorentz was after Faraday by about 50 years.
Actually, it was even earlier. It was the 1830s Faraday was doing the experiments. But we need maybe to divide the possible explanations into two categories, I think, Franklin. One is where you're talking about a sort of an absolute space and some gyroscopic effect, electromagnetic or electrostatic gyroscopic effect from that. Analogous, as I say, to the Troughton and Noble experiment. And I think the explanation you've just given maybe is going in that direction. And as I said, the second part of this video seems to be going in that direction as regards an explanation. That's one category of explanation. And Faraday resorted to that by saying, well, look, the explanation is quite simple, but the magnetic field doesn't rotate with the magnet, so there's an absolutivity there. And that's one type of explanation. Now, the other type of explanation, which I suppose I'm advocating, is a relativistic one, based on Galilean relativity, if you like. Just there must be a relative motion between the magnetic field and the conductor in which any current is to be induced. And all I would do is I would qualify the expression of the Faraday law, because the Faraday law, perhaps as quantified in Maxwell's equation, or Weber's, if you like, the rate of change of flux, just needs to be qualified. It maybe when it is being taught in universities all over the place, that that is correct, but it only applies where there's actually a cutting of the flux by the conductor. So one needs to divide the explanations into those two categories, I think. and maybe make a choice thereafter.
Well, I think this does have something to do with relativity, perhaps.
I would not use the Lorentz force law. I'm trying very hard to give it up completely in favor of, as I mentioned before, the Weber's electrodynamics. And in Weber's electrodynamics, you don't have a magnetic field. So it'd be interesting to have an explanation that is not based around the concept of a magnetic field. And Weber's electrodynamics seems to do that.
How can you do that? Because these things
Because
only happen in the presence of a magnetic field.
all the forces are relative forces. A source charge body and a test charge body. If there is relative motion between the two, there is a force. And that's all there is. And so really it's like, I think Bill Lucas said at one point that there is only one field. Well, in Weber electrodynamics, that's what I'm seeing. There is one field due to the sources, and there's motion of the test particles relative to those charged source particles. And the Weber's force equation simply has that relative motion. And everything comes out of that. And it seems to work out for the unipolar induction motor.
So that would be basically, instead of having your permanent magnet where it's not so obvious where the magnetic field is coming from, you ignore that and replace it with a current loop where it's obvious where that there's a particle generating, charges generating something, right? That's what a lot of these cases do. They replace the permanent magnet with an actual coil of wire where we know that there are moving charges there. That's what's happening. And you're saying if you just calculate everything relative to all those moving charges, then it works out.
Yes.
Okay, well, that's one way of looking at it.
And Franklin, one point that I think I tried to make in one of the memos was, you know, people in our group being anxious maybe to establish any possible contradiction, which in reality would exist with maybe, say, the special theory of relativity. Well, I would be a person in that category. You know, obviously, I believe that there are a myriad of experiments which actually contradict that rather than fulfill it or confirm it. But the thing which I would deprecate would be using this, as I think has been used, this so-called Faraday's paradox, as a possible counter to the special theory of relativity, and saying, aha, therefore it doesn't show because of some absolutivity. So, you know, one has to be very, very careful because one might have a certain predisposition to wish that to happen. But as the previous speaker just said, it seems to be, maybe the simplest explanation anyway, that it is the relative motion between the conductor in which the current is to be induced and the magnetic field, which is in all cases important. And it's only a question of analyzing the details thereafter.
I do have one problem with a special relativity approach to it, and those who don't have the problem, well, fine. But that is if you have two current carrying loops, one above the other, and they're both carrying current, or even if one of them isn't carrying current and only the one, say the upper one is, you know, it would seem to a person, if they were an electron in the lower one, that it might seem that they are moving and the one on top isn't moving. Or if you're in the one on top, you might say, well, the electrons in the lower one are moving. In other words, so that would be the special relativity approach, it seems to me. But in fact, there could very well be some absolutism to this. If the electrons in the lower one are truly absolutely not moving, maybe there's no battery attached to it, then they won't start moving just because there's a steady flow on the upper one. In other words, if they're moving at 2 miles an hour and the one below it is not moving at all regarding the electrons, there'll be no action. There'll be no. But if the lower one is moving in the opposite direction at minus 1 mile per hour, and the upper one is turning the other direction at plus 1 mile an hour, then again there is a 2 mile an hour difference between the electrons in the top and the bottom, and it makes, so I think the special relativity approach, despite Einstein's possibly denying it, is just as confusing as heck, because, as I just showed, it's very relevant which one is absolutely moving regarding the electrons and which one absolutely isn't. In one case, there's no attraction, there's no forces between them. In the other case, there is a huge force between them. And furthermore, when they're moving in the same direction, there's one type of force, and in the opposite, when they're moving in the opposite direction, there's an opposite type of force. So I just think how one seems to be moving with respect to the observer and the other will be a failure, that the special relativity will be a failure. And I think Einstein realized that, which is why he tried to solve the problem with general relativity, which I think still makes it more confusing.
I think the way to solve that is to define motion relative to something else. You cannot have just motion. You can't just say something has a velocity of so many meters per second. It has to always be with respect to something else. And this is why I think in the classical electrodynamics that's usually taught, the definition of the vector potential is not correct, because it is not with respect, the velocity involved is not a relative velocity. It seems to be an absolute velocity, a velocity of the charged particle, the source charged particle, but they're not saying with respect to what. You have to redefine the vector potential so that that velocity is with respect to the test charge or the point of observation. And that makes it a relative quantity, but it breaks the classical electrodynamics. This is all consistent with Weber's electrodynamics, which is inherently a particle-to-particle relationship kind of theory. It's all relative theory. I don't mean special relativity theory. I just mean everything is defined relative to something else. The source relative to the test particle relative to the source.
Well, there is this other video that the second part. So I think I'll show the second part because they try and address this whole relativity thing, basically saying that Einstein is wrong. I'm not sure if I really agree with it, but I think it might be interesting to take a look. So why don't we take a look at that video? Let me put that up and see what they have to say about that.
the first case, we demonstrated 4 scenarios of magnetic induction with the Faraday disk generator. Rotating the disk alone. Then in the second, we rotated the magnet alone. In the third scenario, we rotated the magnet and the disk together. And in the fourth, we rotated the stator alone. The results have led to some controversy since they can be explained by either the magnetic field rotating with the magnet or the magnetic field remaining stationary when the magnet rotates. So which explanation is right? The problem with the generator as currently designed is that for the 8 possible tests that we can perform, the outcomes will be identical if the magnetic field rotates or not. So we can't solve the dilemma using closed circuits. One of the first open circuit approaches was performed by Dr. E.H. Kennard during World War I. Kennard had had a long with Samuel Barnett of the Barnett effect regarding the correct explanation of the Faraday generator. Kennard's paper, published in the Philosophical Magazine in 1917, eliminated the rotating disk and replaced it instead with a rotating capacitor. His apparatus was designed as follows. It consisted of an inner cylinder shown in blue and an outer cylinder shown in beige, which form the 2 plates of the capacitor. These have wires that then lead out of the field to an electrometer. A multi-turn coil is wound around the capacitor as shown by the copper-colored solenoid, and this coil is energized to create the magnetic field that passes through the capacitor, shown by the green loops. The entire apparatus is then rotated together, and the brushes are used to commutate the charge from the generator back to a stationary electrometer. This test apparatus can be understood as a current generated, but rather only the rotating stator leads and capacitor plates experience a Lorentz force when rotated in the magnetic field. The Lorentz force polarizes the capacitor by driving a tiny current on the stator leads, which can't be cancelled by a small current where the disk used to be. This polarization is then measured by a sensitive electrometer. Kennard found that the device generated a polarization of the capacitor even when the capacitor, stator, and magnet rotated together as a unit and the electrometer was at a remote distance. This result appeared to confirm the theory of Lorentz, Maxwell, and Faraday and disprove the theory of Einstein. Kennard said in his final summary,
"An experiment is described showing that a cylindrical condenser rotating inside a magnetized coaxial solenoid becomes charged as required by the theory of Lorentz. Rotation of the solenoid has no effect. The disproof of the moving line theory is thus completed. Electromagnetic induction depends in part upon absolute rotation in the mechanical sense."
This experiment remained largely ignored by the scientific community until it resurfaced again in 1987, this time in the form of a navigational instrument developed by the Department of Defense contractor, the Charles Stark Draper Laboratory. The Keen patent took Kennard's generator to the next logical level, detecting rotation with respect to absolute space for the purpose of inertial navigation. This is because the Kennard device resembles in principle the fiber, whereas the fiber optic gyroscope detects absolute rotation by measuring differences in the arrival time of counter-propagating beams of light. The Keen version detects absolute rotation electromagnetically. The Keen patent provides many more details on the best ways to make the device, including electronic circuitry and even examples of the solenoid construction parameters that work the best. The patent also provided test data to back up their claims. Finally, the Keen patent describes the device as working both with a power supply rotating with the gyroscope or an external power supply, whichever is more convenient. No argument can be made that induction occurs because the power supply lines are cut by a hypothetical rotating magnetic field. After becoming aware of the Keen patent in 2015, I attempted a scientific replication of the device that was cited in Figure 3A of his patent. The device is shown rotating on a turntable in this video. My purpose was to measure the polarization of the capacitor using a battery power supply and data logger that rotated with the device. I also used Keen's method of pulsing the magnetic field so that it would be possible to compare the effect of rotation, the effect of the magnetic field direction, and to contrast with suitable controls, such as pulsing the magnetic field when the rotor was stationary. The data was transmitted by Bluetooth to a computer and then plotted and compared to the original data in the Keen patent. Although my work is still ongoing, the results of data have been consistent with that reported by Keen and Kennard. So the evidence would seem to suggest that. But on a more positive note, the results imply some new and amazing things, namely, magnetic induction does not necessarily need counter movement of a magnet and a conductor. 2, a capacitor may become spontaneously polarized by a magnetic field simply by the rotation of the Earth. And 3, an appropriately designed unipolar generator can detect rotation with respect to the fixed stars, just like the fiber optic gyroscope or the Foucault pendulum.
Okay, now hopefully you're able to hear that, since there was a lot of narration in that video. But now my comments would be that, the main question here was whether the field lines rotated with the magnet, and that's what the relativists would say. And so the conclusion there was that Einstein was wrong. The magnetic field lines do not rotate with the magnet. And this also showed removing the disk from the unipolar generator. And this shows just the case where just the galvanometer circuit is cutting the magnetic field lines. And that was my other point, saying that there may be 2 completely different sources of the EMF, one from rotating disk and one from moving just a circuit through the magnetic field. And this particular experiment eliminates the disk possibility. So what other comments did people have about that video?
Well, I think the video just confuses the issue, and I think introducing it is really basically just creating additional confusion, which we really don't need.
This is Bill Lucas. The reason why Einstein was working on general theory of relativity is because he knew that special relativity could not handle rotation, because rotation involves acceleration, and special relativity doesn't have any effect for rotation or acceleration, and so you can't apply it to experiments that involve rotation. And in experiments in accelerators, we know that any theory that's going to deal with electrodynamics has to not only have things of proportional to the radial separation, but also the relative velocity, but also the relative acceleration, and the first derivative of acceleration with respect to time. So you get what's called radiation reaction. And Einstein was never completely happy with his general theory of relativity because he couldn't take into account radiation reaction. He did include some acceleration. But so if you just look at what Einstein himself thought about these theories, you realize all of them, both special and general relativity, are incomplete because they don't have all the minimal necessary functionality to describe radiation. And so, you can't expect it to explain all the experiments.
Well, what did this video demonstrate, Bill? Do you know what the video demonstrated? I'm not really sure exactly.
Well, you've got disks rotating and things of that sort. Special relativity can't explain
I don't know there was a rotating disk. I thought there was a rotating solenoid.
Yeah, well, a solenoid. Relativity can't explain that. And neither can Maxwell's equation.
Let's go back to what the video said. The video said that Einstein said that the field rotated with the magnet. Is that what I heard? Did you hear that? I was confused about that.
I don't know if Einstein said that, but I know he said that his work was incomplete because it couldn't take into account any rotational effects.
Well, I think they were trying to make the point that if you believed Einstein, then you shouldn't be able to determine your absolute orientation with respect to the stars. But the device that they had in their patented devices was able to detect your absolute orientation with respect to the stars, which would establish a preferred frame of reference, I think.
Well, just a couple of points. First of all, the first video claimed that Einstein said the field rotated with the magnet in contradistinction to what Maxwell said. Maxwell said that it didn't. Now, I don't know if either of those statements is true.
You mean Faraday? Faraday.
No, Maxwell. If you look at the slide, Harry, just at the beginning of the first video, you'll find a picture of Einstein on the left and Maxwell on the right. And
yeah, but it was Faraday who it was Faraday who did the experiment, right?
Yes, I know that. I know that it was Faraday, but the video says it was Maxwell, so I think that's probably incorrect. Yeah, we agreed earlier it was Faraday. Now, the other thing about sensing absolute rotation, that's what I think the second video, as I said, I think sort of conflates some of these ideas, because you can make a mechanical gyroscope. You know, we have a sort of an inertia, and we have a sort of a Newton's bucket system, and we have we have an absolutivity to rotation, if you like. So we can sense that. We can sense the movement of an aircraft using an inertial gyroscope. Now we can substitute for that an electromagnetic gyroscope using a sort of a Sagnac effect thing, because we know that an electromagnetic signal traveling, if you like, that's the slide I was talking about. I'm not claiming it's true. I'm just saying what he said. We know that it's moving, if you like, to postulate it in ether, and if there's relative motion in 3 dimensions, either pitch, roll, or yaw, well, the speed of light actually changes, and this is one of the conflicts with special theory of relativity. So we can measure the absolute speed of an aircraft with an optical gyroscope, and this is actually what's used nowadays in most aircraft. It's probably true that the Troughton and Noble system, where you have a freely suspended capacitor which can rotate about a vertical axis, will actually, through moving through the ether because of the Earth's motion, experience a torque owing to this magnetic field. Troughton and Noble actually measured a very, very small effect, a bit like Michelson-Morley, and it was dismissed. They said it was random, but perhaps that was the effect due to the diurnal spinning of the Earth rather than the revolution about the Sun. It was about 3.4 centimeters, whereas they were expecting 68 centimeters, I think. Now, but the video extrapolates that to saying you can construct an electromagnetic gyroscope from a Faraday generator. Now, I think that's a step probably too far. You know, he's just assuming that because you have the other type of gyroscopes, or he talks about the Foucault pendulum as well. Because you have mechanical and you have electromagnetic. Therefore, this is equivalent, and it's actually an electromagnetic gyroscope, and therefore there's an absolute space. So I think these things are different phenomena, and that's where I would quibble with the second video. And the slide you have up with regard to the first video, I indeed would quibble on that as well. I'm not sure if either of those expressions is correct.
This is Corey. See, Einstein did say that you could establish the rotation and stuff with respect to the stars. He began by basing his principles on the idea of Mach's principle, where that was the case. That's one point. The other point is that if the magnetic field does rotate with the magnet, and it does in my view, and I think it does in Einstein's view, and it probably does in several other people's views. The point is that the magnetic flux flow is from north to south, within south to the north and within the magnet, and north to south outside the magnet as it circles around the circuit. What's important here is how fast does that magnetic field establish itself in the space because the magnetic field, if it establishes itself in space at the speed of light or faster, so if you were to put a magnet in place, how long does it take for that magnet to permeate space? It permeates it, if it permeates it at the speed of light or faster, then the flow of that flux from north to south through that disk is at the speed of light, which is almost instant as far as the rotational speed of the disk goes. So you're cutting that flux line, and as far as it's concerned, unless you're rotating that disk at near the speed of light, it's not going to notice the difference as to whether that magnet is rotating or not. And that's basically it. It's all about the perpendicularity of the electrons in the disk passing perpendicular to the flux flow of the magnet that creates the EMF in the disk that is towards or away from the axis of rotation. And so it really doesn't matter at the speeds we're looking at whether the magnet is rotating or not. And it's hard to tell then from that whether the field is rotating with the magnet or not. Now, in my view, all fields rotate with the particles that they're associated with, because all particles and fields are the same. But that's my specific view. But that establishes that the field does rotate with the particles or with the magnet. But because of the speed, you can't tell that it is.
Well, I think perhaps part of the difficulty here is that when we look at pictures of the conventional field lines, they show them, pointing out of the North Pole in a straight up direction, which is the orientation that we have in these experiments. So we are tempted to believe that those lines are like rotating around. So like here's a picture, standard picture of a magnet. You got your north, your south, and you have your magnetic field lines coming around. And you can imagine that if we were to make this in 3D and we were to spin this around, that these field lines would be moving around, and that those are the things that are doing the cutting. That whatever we detect up here in the North Pole doesn't seem to change at all when this magnet is rotating. So one possible way of getting around this, I was thinking, was that we just simply have defined the magnetic field lines in the wrong direction. Now, this is, of course, speculation, but if the magnetic field lines actually followed the coils of a wire, which is what generates a magnetic field in a solenoid, like we have on this left side here, then we would think that if we spun this around, that there would be absolutely no difference in the character of the magnetic field if this wire was spun around. So that is, I present that as one possible way to intuitively see that there is no change in the magnetic field whatsoever when you rotate around the pole, because the magnetic field lines go in the same direction as the wire that is creating them. That's one possible.
But how fast do you feel if the magnetic flux, and the magnetic flux is circular and flows around the circuit just like an electron flows around an electrical circuit, electrons field pattern flows around electrical circuit. They both flow around the circuit. The electron's field flows through the wire fast or around the wire at near the speed of light. The charge field does, as does the magnetic field flow around the magnet. Makes a complete circuit from north to south, just like electrical charge makes a complete circuit around the circuit. It's just that the flux lines are magnetic flux lines, and if they're moving at the speed of light, then, like I said, the rotational speeds we're looking at is indistinguishable whether they're really moving or not as they're cutting through the disk. And magnetic flux lines magnetic flux is supposed to flow. Like I said, how fast do you believe the magnetic field establishes itself in the space? And it's kind of like how fast do you believe a charge field establishes itself in space? How fast do you feel that the gravitational field establishes itself in space? all of them seem to move at the speed of light or faster. So again, the rotation of that disk cutting those lines is negligible speed. The electrons in the disk, well, the electrons in the wire, for instance, migrate down the wire at almost a snail's pace. So when we're rotating that disk, those electrons that are embedded in those free electrons that are embedded in that material are moving at the speed of the disk itself, which is typically actually probably a lot faster than the speed of an individual electron migrating through a copper wire. So we're actually pushing those electrons almost faster than you'd see them normally in an electrical wire.
Well, I'm not sure if I really understand.
These fields establish themselves electrostatic, magnetic, or gravitational at orders of magnitude greater than the speed of light. But notwithstanding that, I don't see any reason why a revolving element at a very slow speed relative to that would not still be sensible. I mean, if you take say a lighthouse light, which is rotating, maybe once a minute or something around a circumference, you have electromagnetic radiation or photons which are going out at the speed of light, and this thing is moving around very, very slowly. But you still have a sensible motion of the photons, if you like, which are moving around. So this would be my nearest analogy to the.
Right, I agree. I mean, and it would be a sensible motion, but in the fact that until you approach the speed of light, that difference in sensible motion as to whether the magnet is moving or not is not going to be detectable in the slight change in current. The change in current at the speeds we're talking about versus the magnet standing still are so minusculely small relative to the speed of that field establishing itself in the space that we won't notice it until that magnet begins to feed the system begins to rotate at the speed at or near the speed of light. Does that make sense?
Well, actually, to a certain extent, it does. The video itself says that the experiments cannot really distinguish, his experiments anyway, cannot distinguish one case from the other. And, I think it's a question more of analyzing all these very detailed experiments and looking at the simplest explanation. And the simplest explanation would be based on a theory. And the theory which seems to stand up would be that the field is actually rotating with the magnet. I think that's also intuitive, but I mean, you can argue as you do that it's not obvious by any means.
Well, didn't all the experiments just contradict that? That all the experiments show that the field is not rotating with the magnet, that we cannot detect any difference.
No, the experiments just show that at the speeds we're talking about, we can't detect it.
Yes.
And I believe Zian does that those fields actually establish each other at speeds that are faster than the speed of light. But that's an alternate discussion too.
I'm just talking about the Faraday, the unipolar. It didn't matter whether the magnet was moving or not to the experiment. So that would show that
Pardon me, let me talk. You created a confusion in the discussion when you presented the video, the first video. Then you confused things by presenting a second video, which said something completely different and didn't make any sense. So which video are we talking about?
I don't think we're talking about any video. We're talking about, because I'm not sure exactly what the second video is saying. And the first video just clearly demonstrates experimental results. And the question that was on the slide was, does the magnetic field lines move with the magnet? And my point was that it seems that all the experiments show that it doesn't matter whether the magnet is moving or not. That would suggest that it doesn't move.
Let me stop the discussion right here. Okay, let me go over it. That's what Faraday said. Faraday did some experiments in the 1830s, 1831, 32, I think, in which he announced the discovery of electromagnetic induction. And in those experiments, he had some things that he couldn't quite explain. And then in 1851 or 2, somewhere in there, he did a bunch of experiments on this unipolar induction issue, this problem of interpretation that he discovered. He wasn't really quite satisfied. and he did a whole bunch of experiments again. Okay. And he said in his conclusion that the field lines did not rotate with the magnet, which we discussed earlier and concluded was kind of an ad hoc hypothesis. Then later, towards the end of the 19th century, this fellow Tolliver Preston, okay, took issue with everybody saying that the field lines didn't rotate with the magnet. Okay. And he disputed that, and the whole controversy and all these people started arguing about it again. Okay. Well, that never really got resolved, and Einstein came along in 1905, and he threw another complete issue into it. He said the question of whether they rotated or not was meaningless. Meaningless. In other words, it didn't matter. So he was apparently agreeing with Faraday. So then they did a whole bunch of experiments again and started arguing about it again. Okay, I could go on. What happens is that people have been arguing about this, whether the field lines rotate or not. And one guy would produce an experiment, and another guy would say, no, no, no. And that's kind of what's going on. Now they're calling it Faraday's paradox. Okay? And that's kind of, do you understand what I just said? Do you understand kind of how this whole thing evolved?
Well, that's an interesting historical perspective. I would say that I am in Faraday's camp.
Now you have a couple of different issues. Let me just say, you have a couple of, now you have this confused issue. Now, okay, do the field lines rotate or not? That's one question. Then you got this whole business about Einstein's attempt to, and a lot of people, because they believe in special relativity and Einstein, they say, okay, well, Einstein had the right solution, and that creates more confusion. So you're talking about a lot of different interpretations, and so now we've thrown them all into a box and talking about all these different, you know, the Ampere theory got discussed, you know, and so now we got this box full of all these different theories and not really looking at any of the experiments. We're just talking about theories. Let's talk about experiments.
We really just have two questions, and that is, do the field lines rotate with the magnet, and does the experiment have the capability of detecting whether that's occurring or not?
Well, there have been experiments that show that.
I'm just saying those are the two questions we really have that need to be answered.
I think that question's been answered. I think that question has been answered pretty clearly.
Okay, do the field lines rotate with a magnet then?
As I said.
Do the field lines rotate with a magnet then? Do the field lines rotate with the magnet then?
Yes.
Okay, so you say yes.
I
have a tendency to agree with that.
I have a problem.
Can the experiment detect that?
That's a good question.
Only if you alter the magnet so that the magnetic field is asymmetrical, so that when the magnet rotates around, the intense flux of the field changes with the rotation of the magnet. When that happens, you can detect the change in the magnetic field.
Okay, I agree with that.
But that's not the same as experiment in unipolar induction.
But what we just said is that the experiment as it is cannot detect it. And I agree with that too. So there's two answers that we are asserting here, and is that the magnetic field does rotate with the magnet, and secondly, that the experiment as it is can't detect that. So we're in agreement with that.
I am a little bit confused by that, and here's the reason. When a question, when one thinks they're raising a question, does the magnetic lines of this or that rotate with the spinning magnet or whatever? Whenever you talk about a field, in many people's opinion, is just a convenient abstract thing, and you have to ask, it seems to me, what is the nature of the real existence of a magnetic field in order to discuss whether it's cut by anything, or and so on in the physical world. So that is, I'm sorry if this confuses things, but it seems to me that it's an artifact, and when you say, is it cut or is it not cut, that question is an artifact too, because it seems ultimately what you're really talking about is what is really going on with the thing that is causing the magnetic field upon something else that is postulated to cause a field. But the field is a perfectly postulated thing until you can find it and establish it mechanically, as well as the electron movement and so on, which I think is rather well established mechanically.
I would agree with that. What you're saying is what.
Can I talk to you?
Well, just a minute, Harry. I mean, what you're saying here, is very accurate. You have to establish what the field is, how the field establishes itself, and the same is true of what the electron is and how the electron establishes itself. But that goes much deeper than what we're trying to discuss here, and could lead into a lot more varied theories than this particular subject would cover. So I agree with you. You do need to understand what those constituent components are consisting of, but that in itself is a rather extensive discussion. And I don't know if we would ever get to the end of that right away, but it certainly is something we should dissect a piece at a time, but not all in the context of this experiment, would be my opinion.
Well, gentlemen, we are not looking at things very well, because all the data from accelerators, which is more fundamental than these experiments that we're doing in the lab with coils and magnets, you've completely ignored all of that. And they have answered a lot of these questions. And first of all, getting back to, there are 3 types of electric and 3 types of magnetic fields. One type cannot be shielded.
Now you're digging into exactly what we were talking about earlier.
There's a tensile strength to certain fields. You have ignored that. That will tell you which rotates with something like a magnet that rotates, or a coil, which part of the which type of electromagnetic field is going to rotate with it and which type won't. And so those have all been determined by experiments with accelerators. But I don't think any of you have any experience in that area.
No, it's not being ignored. It's just the fact that that's too great of depth to consider in this short, brief discussion.
Well, anyway, that's my background. So,
well, Bill, maybe you could tell us then, what basically do those accelerator experiments show with regard to where the seat of the EMF is, in the magnet or otherwise?
Well, when electrodynamics was developed, the things that were measured were fields. The concept of charge was a convenient concept to be able to write down an equation. And so charge is something that we don't observe directly. So it's a idealization. And
well, I would disagree with that.
When we do experiments, we find that charge is never isolated. What we call charge is always interacting with everything in the universe. And what enables that to happen is the field with tensile strength. There was always a question in electrodynamics and in gravity is, how could the force, electrodynamic force, be propagated through a vacuum? And of course, the answer was the electromagnetic field goes everywhere. You can't shield it. Certain types of it you can't shield. So the field is everywhere, and the field is more fundamental than the charge. So we're putting a lot of emphasis, like today, on the movement of charge and the charge in a magnet and that sort of thing, when in reality we're not taking into account the effect of the field at all different distances. And so, for instance, you have the effect on a field with the rotation of the Earth moving around the sun moving around the center of the Milky Way galaxy, the Milky Way galaxy moving around some other center. And so all of those things can be measured with fields. But we don't like to acknowledge that because it falsifies most of our theories in modern science, like special and general relativity theory and the Oliver Heaviside version of electrodynamics. And,
Bill, I don't have any disagreement with what you're saying about, a matter of fact, you talk about tensile strength of the field, and I talk about nothing but a tension field. So I have no disagreement with that. I'm just saying that, how those fields define how the energies move in those fields and stuff like that is a very in-depth discussion. Even the complexity of how the fields move to create an electron in that, and how the fields move to create a magnetic field, how those happen are such great depth compared to the surface stuff we're trying to talk about now, as to how those particular characteristics of the field interact with each other. That's what gets very difficult, because there's going to be a very great variation in how you see the field interacting to make an electron and how I see the field interacting to make an electron.
I mean, I would tend to agree with that, because we have things, because this is like a bulk experiment with, not that very complicated. But we also have things that we accept as truisms, like the Lorentz force law, so I can build my little model here that shows what's going on with the Lorentz force law. And just using these two, we can try and explain what's going on with unipolar induction. I mean, listening to the whole conversation here, I can only give my opinion, but my opinion is that I don't believe that the nature of the magnetic field, whatever it is, changes with rotation around the pole. And that the Lorentz force law, the little arrow here that says magnet, doesn't have to do anything with velocity. It only has to do with the direction of the field as defined. And so I would think that by any stretch of the imagination, any kind of rotation wouldn't matter. The rotation of the magnetic field line is not anywhere included in the Lorentz force law. So I would think it just simply doesn't apply. In which case, the force flag here would say that the electrons are still going to migrate across the disk, whether the magnet's moving or not. That's kind of what I'm concluding. I don't know what other people are concluding, but.
Well,
so
your little pencil diagram, is a very accurate, is an accurate representation of Lorentz force law. What needs to be, and what Bill is talking about, and we're saying is that what needs to be understood is how the electron displays those properties that make those fields act orthogonal to each other. How that comes about, and that is all about the characteristic patterns, energy patterns within the electron, how you can take one force and create a force that comes exactly orthogonal to that when you encounter the electron, and so that needs to be established in what is the nature of the electron itself, and what is the nature of the electron that creates the magnetic field that also has such polarization to it. And it's those polarization things that are much deeper than what we're discussing now. If we just stick with the right-hand rule, which your pencil demonstrates there, and trust that that's true, then we'd look at the flux flows and the electron flows, and don't necessarily need to go into the in-depth understanding of what the electron field is and what the magnetic field is. And that's the surface level that we're currently at. To dig deeper would take much longer than the 2 hours we've got.
Yeah, well, we could dig into that, but I'm not aware of any convincing theory, including my own, that explains this thing.
Well, I think Bill has a fairly good concept with his moving wave pattern of the electrons. Slobodan also has a fairly good concept with his.
No, I think that all breaks down when you actually try and physically explain this thing.
Basically, because all of those characteristics are showing there's some kind of rotation within the field. Bill's is, Slobodan's is, mine is, We have Roy and Ron Hatch's electron demonstration. All of those electron patterns demonstrate one type of rotation or the other, and the rotation of the field is one of the key points as to why you can get that orthogonal action where energy comes in at one angle.
Well, see, you
can
explain things like that in a very wordy fashion.
Correct.
But you have to explain, in order to do Lorentz force law, you have to explain two parallel wires. When they're going the same direction, they attract. When they're going the opposite direction, they repel. Now, you have to come up with a mechanical reason to explain just that.
And that's exactly what we've all done by establishing the rotational characteristic of the electron.
I do agree with that to some extent, and it's an interesting. I want to make a weak analogy, at least, to that pencil and the papers going in the two orthogonal directions. A gyroscope will spin, and we consider angular momentum to be in one direction, so we draw one vector, say pointing up. Then if you try to tilt the gyro, that will you can draw another vector, say off to the right or left. And then finally, when you try to move it to the right or left, tilt it to the right or left, there is something called precession, which is still the third orthogonal vector that is parallel to, is perpendicular to both those vectors I just described. So I would certainly second the motion that rotation is involved.
Yeah, and it's a very good example of the gyroscope of the characteristics of the orthogonal forces. Another simple one, and it only deals with rotation in a single plane, would be even just a baseball, a knuckleball being thrown, having a spin on it as it encounters the atmosphere, having a curve because of the spin on the axis. And that's a very simplistic.
Do you have any experiments to demonstrate that?
Any what's that?
Got any experiments to demonstrate that?
How a knuckleball?
Any experiments that show that?
How a knuckleball works?
I don't see what this has to do with anything. Do we have experiments that we can point to that we can explain consistently based on your theory?
Oh yeah, definitely. Because anytime an electron moves,
all I'm hearing is like I'm going to try to explain this particular set of experiments. No, that's not what the problem is. You have to explain a lot of experiments in addition to the particular experiment shown in the video, and they have to all be consistent. That's the problem.
Anytime you take an electron and you take an electron in a vacuum tube,
You're not talking about experiments. You're talking about an electron. I have no idea what you're talking about.
Harry,
let's not talk about theory. Let's talk about what experiments do you need to basically come up with a theory.
Well, does an electron deflect in the presence of a magnetic field in a cathode ray tube?
Well, I would just challenge. Maybe we'll do this next week.
So which direction does it deflect?
We're kind of getting to the end of the hour here. So, but I would challenge anybody to explain how the Lorentz force law works in a rigorous fashion.
Okay.
Which means that the important things are that if there's no velocity, there's no force. That's one of the hardest things that you have to deal with. That there's no velocity means there's no force.
It's no problem. But you have
to like to try and explain that?
The problem that the
absolutely
law violates Newton's third law or something. It's Newton's third law. There's no action and reaction equal.
It can be explained.
Well, I would love to hear your explanation. Would you like to do that next week for us?
Well, I don't know what my schedule is next week, and I don't have any diagrams or ability to do that. I would like to verbally. I can explain it.
But even before addressing that, could I just ask, getting back to the rotating field again, have we reached any consensus today about that? I mean, I think we've agreed on previous occasions that it's not simply a question of what the majority thinks and voting for a particular case. However, it appears to me that most of us, if not almost all of us, would consider that the simplest explanation of the experimental results, the detailed experiments, is that the magnetic field moves with the magnet. I think Corey says there are some difficulties in looking at that because of the speeds, but he believes that. I think Bill believed that as well from the accelerator experiments. Please correct me if I'm misinterpreting anybody. But I think you, Franklin, maybe dissent from that, if I understand.
Yes, I'm dissenting. I'm thinking it doesn't matter.
You're dissenting from the dissenters. So
because the Lorentz force law doesn't say anything about the motion.
Yeah, well, we'll have to give that some thought. But I'm just wondering,
whether it's moving or not, it's irrelevant.
Yeah, well, what you're saying is not detectable, not that doesn't matter. But yeah, continue, Ian.
Yeah, no. I think the Lorentz law is just another way of looking at it. It's a sort of a relativistic way of looking at it. You're looking at the velocity and then the actual field and then the force. I mean, in the very first paragraph of Einstein's 1903 paper, he says this. He says that there are asymmetries which appear not to be inherent in the case. So I think the Lorentz law is merely a way of trying to address this. And, you know, if you look at the sort of mathematics, it's like, you know, you're getting it from both frames of reference and you're getting the same thing. But as regards the physical explanation, we can give that more thought if you want to, Franklin. I'm just wondering, is there any substantive view here from today's thinking that the field induced by a magnet, or the field produced by a magnet, does not actually rotate when the magnet is
Okay, I'm going to give someone a chance. I'm going to pick on Jim. So Jim, I'm going to unmute you. I'm going to give you the last word. So, does the magnetic field lines rotate with the magnet based on everything you've been learning, just lurking here?
I don't know, but I think we should really look at that invention that guy mentioned. I think you know, I'm an ether guy, so I think it all depends on the ether.
All right, so Jim is just as confused as ever before, but I think that as a science chat, it's just up to us to listen to the various different arguments which we've had today and decide for ourselves. Like, you know, I've already given my opinion, and that's just my opinion.
Why don't you look at experiments, Franklin?
I've looked at all the experiments that
I've heard lots of opinions, but I haven't heard anybody that's got experiments to back them up.
We've just been looking at the unipolar experiment. That's what we're trying to back up our thoughts with.
Everybody's got an opinion, but you need to base your opinion on an experiment.
And it's the unipolar induction experiment.
That's just one experiment. There have been others experiments that have been done. Why are we just talking about one set of experiments that could be completely misleading?
Because we're trying to explain how that particular experiment works. We're not trying to explain how, say, Lorentz force law works.
Which is very difficult to do unless you look at the other experiments that other people have done. And I explained to you what those experiments show, and those experiments show that the field rotates with the magnet. That's pretty well established by experiments, and yet you're still questioning it.
Well, my point is it doesn't matter. According to Lorentz force law, it doesn't matter what the field lines are doing. The only thing that matters is their vector direction.
Now you've changed the subject.
That's because I've come up with a completely unique solution.
Don't you think we should base our opinions on what experiments show?
Yes, experiments show that the Lorentz force law is correct. And if you apply the Lorentz force law to the unipolar induction situation, then it seems that everything works out. There's no contradiction.
But the video that you just presented here at the beginning of this whole discussion says what you just concluded was not true. So you're just saying words.
No, all we have from the video is an experimental result. That we know there are EMF.
You have no basis for anything that you're saying that comes out of your mouth.
No, I absolutely do. We have the Lorentz force law. We apply that to the situation we see, the mechanical situation we see, and we can make direct predictions about what we think should be.
Experiments, Franklin, that basically substantiate what you say. Please.
That entire video substantiates what I say. The experimental result, which shows that the rotation of the magnet doesn't matter, substantiates what I say. I mean, if anything, that's what that video shows, is that in that situation, the rotation of the magnet makes no difference at all. And the only way that I can see it being explained is that it just doesn't matter. I mean, even if the magnetic lines did rotate, it still wouldn't matter. That's not a component in the Lorentz force law. So it's not a paradox to me.
So how are you going to explain the Lorentz force law when the motion of the magnetic field doesn't matter?
Well, I gave one possible explanation, which is that the nature of the magnetic field doesn't change with rotation.
Let's get some experiments. Let's talk about experiments.
Yes, all the experiments show that the rotation of circular magnet does not make any difference upon the nature of the magnetic field. That's what experiments, at least the ones that we've looked at in this discussion, show.
Well, what happens if I'm rotating an asymmetric magnetic field?
Then it would be asymmetric, and you would expect the EMF. You would totally expect that.
No, you would expect the EMF to change.
Yes, I would expect it. It's an asymmetric magnet.
So
I would totally expect the EMF to change. No, the thing is that if it's symmetric, then it will not change. This is what we're establishing. If it's symmetric, it will not change. If it's asymmetric, of course it will change.
Oh, great. Now you begin to understand it. Thank you.
By the way, I've been rather pushing some of Kelly's expositions and his own experiments. Many of his experiments have not been heretofore done. And I gave a reference to his book. But if you don't have that at hand, if you look at Harry's detailed paper that he sent out recently, he actually refers to, I think, Harry, to Kelly, reference 9 or something, I think it was. And there's a link there. If you click on that, you'll find online Kelly's monographs. So you don't need to buy his book even to get this chapter 9. It's essentially the same. I've had a look at it. So you might like to do that at your leisure. Anybody on this call.
All right. Well, we are at the top of the hour today. So I'd like to thank everyone for participating in our discussion of unipolar induction and how that works. So I don't know that we ever came to any real conclusions, but we were just here to just dig around and find out what the issues are, and it's once again who is going to be most convincing as to what is the explanation for how this goes. So thank you for your participation, and maybe we will continue discussing the magnetic field. If anyone would like to explain how this works, I think that would be an interesting challenge. And that will do it for this week. Thank you.